Now remember what theorem 0.22 said. Between any two real numbers, there's a rational number. Well, that actually implies something much greater than that. It implies that every interval, AB, contains infinitely many rational numbers. I won't formally prove this, but if there exists only finite rational numbers in the interval AB, that means we can label them, we can number them. Rational number 1, rational number 2, through n. We would have A less than, I'll use Q for rational numbers, lowercase q. So if there's a finite number, we're allowed to just list them out like this. But do you see the contradiction here? If the only rational numbers between A and B are these irrational numbers, well, what about this? The interval Q1, Q2 has Q1 less than Q2. So therefore, there's a rational number inside this interval. So we missed one. In fact, we missed infinitely many. So every interval like this, where A is less than B, has an infinite number of rational numbers. Now some facts. Q, we've already seen, is a countable set. Countable set. But R is uncountable. The real line, the number of, the set, the real numbers, is an uncountable set, where Q, the rational numbers, is a countable set. What about the irrational numbers? I don't really have a letter that I use for the irrational numbers. I guess you could use a capital I. I typically write the irrational numbers to be this, R minus Q. It's the real numbers, take away the rationals, and what you're left with is the irrationals. And this is also an uncountable set. All right, let's take a look at theorem 0.23. If little r is a real number, and let's make it positive, r greater than 0, then there exists another number, we'll call it x, in the real numbers such that x squared equals r. Pretty simple statement. Basically, all that's saying is that every positive real number has a square root. The proof, I'm going to let you look at that. It's in the text. Now the sketch, I'll do just a couple of lines of the proof to give you the flavor of it. Let's just say for now that r is greater than or equal to 1. If it were between 0 and 1, it's just a slightly different proof. I'm just going to look at this part of the proof. Let's say that r is at least 1. Let's let capital A be this set. The set of all z and r. In other words, a set of all real numbers z, such that z is greater than 0 and z squared is less than or equal to r. Well, it turns out that x is equal to the supremum of that set A. And we know that set exists, it's real numbers, it's bounded, therefore it has a supremum. And the next thing I was going to write down, I already wrote down. Oh no, this is slightly different. Radical 2 is, we know it's not a rational number, now we know it's an irrational number. Radical 2 is an element of the set of the irrational numbers, the reals minus the rational numbers. And that can be proven by theorem 0.18 and theorem 0.23. All right, I'm going to squeeze one more, if I can, short theorem. Oh, I think I need a little bit more room. I'll save it for the next video.